All right, this is a video on solving systems of quadratic equations, and we'll start off with a brief introduction, but mostly spend our time on solving a couple examples. So as an introduction, a reminder that when we solve a system of equations, we're looking for a point on a graph that are on both functions, that are parts of both functions, that are common to both functions. Really what that means is we're looking for where two lines or curves intersect. We're looking for intersection points. Okay, what we've done in the past so far in Algebra 2 and Algebra 1 is we've really just we've solved systems of equations of linear functions, and we would find, for example, that point, the coordinates of that point right there, the xy coordinates, and those are a number for x and a number for y that work in both equations, okay, that result in valid equalities in both equations. Here, we're going to make things a little more complex and start adding in parabolas. Okay, so we'll do two examples. Our first example is to solve a system of equations where one equation is a quadratic and one equation is linear. And then our second and final example we'll look at has both equations being quadratic. And all the rules we followed before are the same, okay? So you can follow substitution, you can do elimination, you can solve these guys graphically. So lots of solutions, but I just want you to be able to choose the most efficient process. And I think you can see for this first one, since y is isolated for in both equations, it's going to be easiest to simply plug in that red x plus 6 in for the red y, right? Since x plus 6 is equal to y, we're allowed to replace it. So let's go ahead and do it, and we can rewrite this as x plus 6 is equal to negative x squared plus 5x plus 6. And then let's go ahead and solve. And I always like having a positive a value, a positive x squared coefficient. So let's get everything on the left. Let's add x squared to both sides. Let's subtract 5x from both sides. Let's subtract 6 from both sides. Okay, and then let's see what we end up getting. So on the left side, these guys all cancel on the right. On the left side, we have an x squared. For our x terms, it looks like we have a minus 4x. And then it looks like our 6's cancel. So x squared minus 4x is equal to 0. So you might be thinking, let's go do the quadratic formula, but this is actually nicely factorable. Just pull out a GCF. X times the quantity x minus 4 is equal to 0. So using the zero product property, either that x is equal to 0 or that x minus 4 is equal to 0, which would mean that x is equal to 4. So we have two solutions now, x equals 0 and x equals 4. So those are the x values. We would still want to find the y values. So let's plug our x values into either equation. Choose the simpler one, the linear equation, and let's solve for y. Okay, so if x is 4 comma something, we're going to get that something by saying y equals 4 plus 6. We plugged in 4 for x, and so that means y is 10. Our second option had x equal to 0, and so again we'll plug in 0 for x into our linear equation, and 0 plus 6 is 6. So these are the two intersection points on our graph. We found two different points, which we never found with a system of linear equations, right? We only ever found 1 point or 0 points or infinite points. But here we found two discrete points, and let's go ahead and look at the graph on Desmos to confirm. So we are working with these two initial equations that I just turned on, and let's see if I can get the intersection points to show up. So 0, 6 and 4, 10 are the two solutions, the two intersection points for this line and this parabola. All right, we can head back and solve our second example, a little bit more complex. It's a quad-quad system, so both are quadratic examples here. Okay, you might think, or both equations are quadratic, you might think, let's do the elimination method, because if we added the two equations together, the x squared terms would cancel. And the x squared terms would cancel, but we would still have an x and a y in our resulting equation, so we wouldn't have eliminated any variables. So I'm going to go through the same process where I see that this is equal to y, so we're going to plug it in for that y right there. And we will probably have a quadratic formula or maybe some factoring that we'll need to do down the road, but we'll get there when we need to get there. So again, I like having everything over on the left, positive a value, positive x squared coefficient. And so let's add x squared to both sides. Let's add x and subtract 12 from both sides. And let's see what we get. Okay, so on the right side, everything eliminates and goes to 0. On the left side, we have a 2x squared plus 8x. Oh, and we got lucky again. The constant terms canceled out. And so we have a 2x squared plus 8x is equal to 0. This might not be conventional, but I just like dividing by 2 to simplify things down a little bit. And so we get an x squared plus 4x is equal to 0. And so a very similar situation to what we had with our last equation. We can plot a GCF of x, and we get x is equal to 0. So one option is x is 0, and another option is x is negative 4. So if x is 0, we need to go ahead and plug in some x's, okay? So y would equal 0 squared plus 7 times 0 plus 12. I'm choosing what I think is the simpler quadratic equation to plug in my x values to solve for y, okay? And that means that y is then equal to 12. So if x is 0, y is 12. Second option is x was equal to negative 4. So let's go ahead and plug in negative 4 in for x in my quadratic equation. A little bit more math to do here. That's a negative 4 squared plus 7 times negative 4 plus 12. Y equals 16 minus 28 plus 12. Does that turn into 0? Let's check that on a calculator. Yep, it turns into 0. So when x is negative 4, y is 0. And so those would be the two intersection points of these two parabolas. So these two parabolas would intersect in two different locations. So let's go ahead and see if we can check that on decimals. 0, 12, and negative 4, 0. So I'll turn off our first two, turn on our second two, and it looks like we got it, okay? Negative 4, 0, and 0, 12. We probably could have known it was 0, 12 because they both had the same y-intercept of 12, so we know they go through that point. But it was good practice to go through the solution process. So looks like we did it. That was a good one, and that is a good place to stop right there.